So, okay. So some concepts that we want to be sure that we know for the final exam. So I would say first thing would be molecular geometry. So molecular geometry. Okay, so you want to make sure that you understand that when you have a carbon that has 4 single bonds, that it's tetrahedral, and that when you have 2 single bonds and 1 double bond, that it is trigonal planar. And then when you have a single bond and a triple bond, in that case, it's linear, right? And you want to know your bond angles, 109.5 degrees, 120 degrees, and then 180 degrees. But one that's a little trickier is when you're dealing with a nitrogen. So let's say you have the nitrogen in something like a compound like this, where you have a lone pair. Let's say you have a methyl group here. Let's say you have, I don't know, an ethyl group in the background and then coming out in front. Let's say you have, I don't know, an isopropyl group, something like that, okay? So what would be the molecular geometry of this nitrogen? Can anybody tell me? And it's not a trick question. And I can see the chat. Can anybody tell me the molecular geometry here? Yeah, it's trigonal pyramidal, isn't it? Thanks, Jenny. It's trigonal pyramidal. And all you have to know as far as bond angles go is that it's less than 109, less than 109.5 degrees. And that's because of the lone pair, right? It pushes these bonds down a little bit. But then something else that we talked about earlier on in the class is, let's say you had something like, I'll draw an actual compound. Let's say you have something like this, okay, where you have the nitrogen in an amide like this. So I'll just go, like we have this. So this is NN dimethylformamide. So this is actually a solvent that's used a lot of times in organic chemistry. But we know that we could draw a resonance form for this compound where we show this pair of electrons being delocalized. And so our resonance form is going to look like this, where we have a double bond to our nitrogen, like that. And then we have, so we have a negative charge here and a positive charge here. Let me just fix that, make it look a little prettier. So there you go. So now if you look at both of the nitrogens here, in the first one, it looks like it's trigonal pyramidal. But if you look at the second one, it looks like it's trigonal planar, right? Because it looks like this one is sp2 hybridized and it looks like it's sp3 hybridized. Well, something that we covered in chapter 2 was this concept. And we said that, as a matter of fact, the nitrogen in an amide is actually trigonal planar and the hybridization is sp2. The reason we know that is the only way that that lone pair, and I'm talking about this lone pair here, can participate in resonance is if it is in a p orbital. So how do we have a p orbital on there? The only possible way is for that nitrogen to be sp2 hybridized. So the nitrogen in an amide, and this is in an amide, is in fact sp2 hybridized, and its molecular geometry is trigonal planar. And this has a lot of consequences when you study proteins, okay? So later on in organic chemistry, you'll study proteins and peptides. And the fact that there's a lot of double bond character to this carbon-nitrogen bond has a lot of consequences in biochemistry. All right, so that's just a little bit about molecular geometry. Then as far as stability of carbocations and radicals. So we talked a lot about carbocations and radicals, and that what we saw is that they follow the same trend in terms of stability, that tertiary is more stable than secondary, and secondary is more stable than primary, and primary is more stable than methyl. So this is going to be most stable. And then here we have less stable, okay? But then we can have carbocations and radicals that are even more stable than these, okay? So what if we have something that's allylic, okay? And I don't ask my students to compare allylic carbocations, you know, whether it's primary, secondary, or tertiary. I guess you could compare those. But then remember that you have things like benzylic, and allylic, which are even more stable, okay, whether they're primary, secondary, or tertiary. So make sure you're aware of that. All right. Let me think here.
Hey, Mr. D.
Yeah, go ahead.
So there's not going to be a question like a secondary allylic versus like a tertiary.
Oh,
The sec
absolutely. That's totally possible. Yeah.
Okay, would the secondary allylic be more stable than the tertiary then? Yeah.
No, right? Because then you would go back to this. So let's say you had something that's benzylic, right? And then you compare secondary benzylic versus tertiary benzylic. Well, the tertiary benzylic is going to be more stable, right? So it's going to be stabilized via partially hyperconjugation by having more alkyl groups around it. So
I mean, like
the trends
just plain.
the trends go together. Yeah. So if you're saying, are you going to compare a benzylic and a tertiary or something like that, primary benzylic versus tertiary? Again, this is something that we looked at, and a benzylic radical is more stable than a tertiary. Okay.
Yeah, thank you.
All right. Cool. Another one that or something else that I think is pretty important is, let's say you had a compound, something like this. Okay, you have an ester like ethyl acetate, and then you compare that to something like, I don't know, like butanoic acid, right? They have a similar molecular formula. Okay, they have the same molecular formula, as a matter of fact. But if I look at the ester, so ester, what intermolecular forces are going to be experienced in here, okay? Well, every molecule has London forces, okay? We never escape London forces. So this has London forces, and this has London forces. Then what about dipoles? Does the ester have a dipole? Yeah, it's got a couple of dipoles, right? You've got a dipole going in this direction. You've got a dipole going in this direction. And so therefore it has dipole-dipole forces, dipole-dipole. And then if you look at the carboxylic acid, it has dipole-dipole forces as well. So dipole-dipole. And then as far as hydrogen bonding goes, could anybody answer this? Does the ester have hydrogen bonding? So if I had a pure sample of the ester, would it have hydrogen bonding? No, absolutely, right? So no hydrogen bonding. So I won't even write it in here. But in the carboxylic acid, yes, we have hydrogen bonding. Okay. Now, in terms of intermolecular force strength, hydrogen bonding is the strongest. Okay. And the London force is the weakest. Okay. And so if we look at the boiling points of the two of these, that would mean that this compound is going to have a higher boiling point because it has a stronger intermolecular force that the other compound does not have. Okay. Besides these intermolecular forces, you might remember in general chemistry. So if you took general chemistry at UCCS, it would be chemistry 1401 and 1411. You actually talked about more intermolecular forces than the ones that are shown here. Okay. In that, you would also talk about things like ion dipole forces. So ion dipole forces. And what that is, say you have something like, I don't know, say you have something like a carboxylate, right, like this, and then you have a sodium cation. Well, this is an ion, okay, and then you have a dipole here, so you have both of those forces in a compound like that. All right, let's move on. Another thing that you're going to see in your final exam that we've gone over in detail are Condon-Gold Prelog rules, so the designation of RNS for a compound, so make sure you're able to do that. We also talked about things like optically active versus inactive, okay? And if we think about examples of things that would be inactive, this would be something like a meso compound is optically inactive. Also, something with no chiral center would be considered to be optically active. So we covered that in detail. Another thing that you want to be aware of would be Newman projections. So Newman projections, and make sure you understand things like gauche interactions, and anti. Okay, so gauche and anti. Like let's say you had a molecule like butane, like 1, 2, 3, 4, right? So let's say you had something like butane, right? You have a methyl group, And then let's say you have the methyl group down here, and then everything else is a proton, right? This would be, could anybody tell me what conformation the molecule is in here that I've drawn in this Newman projection? What conformation would this one be? Would this be gauche or anti, what I've drawn here? Yeah, this is anti, right? Because the two methyl groups are on opposite sides, so this is anti. Anything else would be a gauche conformation. So let's say I took this, right? So we'll just move it over here. Okay, let's say I get rid of this and this and this. Okay, yeah, let's say we rotate it so that we have the methyl group here, right, like this. Then this is a gauche conformation. So you have these steric interactions here, and this is going to be a gauche interaction. So gauche is going to be higher in energy than anti. Make sure you understand, terms like nucleophile and electrophile. So let's say you're looking at something like an SN2 reaction. Let's say you have something like, one, let's say you have one bromobutane, and then you treat that with something like, I don't know, a hydrosulfide ion like this, okay? Well, I think that everybody could draw the curved arrow, so you get nucleophilic attack, right? Nucleophilic attack, loss of leaving group, and then you end up with your product, which in this case is going to be a thiol, like this. But could anybody, if I highlight this yellow and I highlight this in green, which one is the electrophile? Yellow or green? Yeah, exactly. The green one would be the electrophile, and the yellow one would be the nucleophile, right? Nucleus lover and electron lover. So another thing is, like, let's say you want to write down the rate of the reaction for an SN2, okay? Again, the rate law is going to be rate is equal to K times the concentration of your electrophile times the concentration of your nucleophile. So what that means is if you double the concentration of this, you're going to double the rate. If you double the concentration of this, you're going to double the rate. Give me a thumbs up if you're with me on that, on a rate law. Shah, is everybody with me on that? Okay, it's affected by the concentration of the electrophile, and it's affected by the concentration of the nucleophile. Whereas with an SN1, it doesn't work the same way. So let's say you have an SN1 reaction. Let's say you're taking something like, I don't know, this compound, and then you put it in something like methanol. Okay, this is what we call a solvolysis reaction. Solvolysis reaction, right? Because the solvent is doing the reacting. But remember, in an SN1, it's not a concerted process. It happens one step at a time. First, the leaving group leaves. You would end up with, oh, I can switch my color here. You would end up with this carbocation. So you'd end up with a carbocation that looks like this. And then the nucleophile would come in. And then after the nucleophile comes in, you would end up with this methyl ether that's shown here. Okay, so you'd end up with this compound. Maybe I can fix that bond. Okay, but that's the compound you would end up with. Okay, in this case, so loss of leaving group followed by nucleophilic. So this is nucleophilic attack and proton transfer. I'm not going to draw those steps. But when you write out the rate law for an SN1 reaction, the rate law, this is unimolecular. It's just going to be rate constant times the concentration of your substrate. That's it. There's no methanol involved. So if I was to change the concentration of the methanol, is that going to have any effect on the rate of the reaction? If I change the methanol concentration, will that do anything? No, it does nothing to it whatsoever. Okay, so that's an SN1 reaction. That's a solvolysis reaction. And remember, it's a unimolecular process. Now, as far as the rate determining step, okay, we talked about SN1 rate determining step. Does anybody remember out of all these steps? So there's 3 steps. There's loss of leaving group, there's nucleophilic attack, there's proton transfer. Does anybody remember which one of these is the rate determining step? Which one has the highest activation energy? Exactly, Raoul. It's the loss of leaving group. This one has the highest activation energy. There you go. All right, so a little bit of SN1 reactions. Another thing that I would review, so I would just know your pKa's. So review pKa's in chapter 4. You want to make sure that if you're given a compound, like, something like this, and then you have some, right? You want to make sure that you're able to determine the difference in pKa between these kinds of protons, whether it's an alkyl proton, which is around 50, or a vinylic, right, which is, in the 40s. So I'll just put, somewhere around 40. And then the alkynyl one is a lot lower. It's 25, and that's why it's so acidic, okay? You should also know the pKa of something like, so I'll put here pKa's. So pKa's. So you want to know carboxylic acid, right? Alcohol, amine, etc. Anything that was in that table of pKa's that we looked at in chapter 4, make sure you're aware of your pKa's. Any pKa that we went over in this class, okay? Yeah, so I'd also review leaving groups. So we spent a lot of time talking about leaving groups, okay? Leaving groups. What is a good leaving group? It's the conjugate base of a strong acid, right? So what are some good leaving groups? Chloride is a good leaving group. Bromide is a good leaving group. Iodide is a good leaving group. Tosylate, that's a good leaving group. Water is a good leaving group, right? It's the conjugate base of hydronium, which is a strong acid, etc. So make sure you're aware of when something is a leaving group and when it's not a leaving group. Let's see here. I would also go back to SN1 and SN2 and say, for E1 and E2, is that whenever you see the 1, this means it is a stepwise, right? Stepwise. The reaction happens one step at a time. So that's first order. If it's second order, okay? If it's second order, that means it's concerted. And concerted is just a fancy word for everything happens at the same time. The nucleophilic attack, the loss of leaving group, they occur simultaneously. What else? So SN1, SN2. We went over ring expansion last class, so you guys know that pretty well. I would go back and review all of your reactions from chapter 8. So chapter 7, 8, 9, 10 reactions. All the different reactions that we looked at, whether it was halohydrin formation, Markovnikov addition of water, avoiding a carbocation rearrangement, right? Oxymercuration, demercuration, halohydrin formation, bromination, Markovnikov addition of HBr, anti-Markovnikov addition of HBr, hydroboration, oxidation, dihydroxylation, etc. SN1, SN2, E1, E2, primary, secondary, tertiary alkyl halide. The table that has a strong base, weak nucleophile, strong base, strong nucleophile, strong nucleophile, weak base, weak nucleophile. Make sure you review those tables and you're aware of all the different reactions that we looked at. That covers a huge chunk of just the material. In the spectroscopy section, so for chapter 15, if you were paying attention this morning, which I know you all were, when we looked at the spectroscopy problems in the ACS study guide, the problems that you're going to see are going to be in the same kind of vein, right? Nothing earth-shattering there. Also, I would look at the chapter 10 reactions, right? In chapter 10, we covered a couple of reactions. We covered halogenation, so halogenation. Then we covered anti-Markovnikov addition of HBr, and we went over the mechanism for that. So make sure you review that mechanism. And then we also talked about allylic bromination. Okay, so make sure you review all three of those. Acid-base chemistry. So I would make sure that you know what an acid, a base is, that you can identify a conjugate acid and a conjugate base, right? This is something that you would have learned in General Chemistry 1, but we covered in this class as well. Also aereo. So I would review the concept of aereo and have an understanding, because aereo can get you out of a lot of problems in organic chemistry. I would also not only cover, when it comes to acid bases, I would also, in this class, we mostly focus on Bronsted, right? We spend probably 95% of our time talking about Bronsted acids and bases, but I would also be sure to know Lewis acids and bases and Arrhenius acids and bases, right? Those are the three definitions of acids and bases that we looked at all through organic chemistry. Lewis structures, we reviewed some of those yesterday when we looked at the ACS study guide. So, Lewis structures, that has never gone away. That was a big part of General Chemistry 1. I'd say Gen Chem 1 and this class, Chemistry 3101. Did we talk about Lewis structures or what? It's like we never stopped drawing them. It was all we did was draw Lewis structure this and Lewis structure that, it seems like. Carbocations, I've gone over that. Activation energy. So being able to read a reaction coordinate diagram. So let me just erase this here. Oops. So make sure you can, just look at a reaction coordinate diagram like this. So we have, reaction coordinate here. Yeah, we'll just put reaction coordinate. We'll just put energy over here. So make sure you understand if you have an exothermic reaction. So this would be exothermic versus if you have an endothermic reaction, is going to look something like this. Okay, make sure you're aware that the activation energy for this reaction is all of this, whereas for the blue one, the activation energy is a lot lower. Okay, so this is your activation energy here. So nothing really new in terms of reaction coordinates, just your reactions, alkylations, and all that kind of stuff. And I would say that's kind of a Sparks Notes version, but those are the major concepts that you want to be aware of, for the exam.